Hello, this is Paul from Foresight Tech. In this lecture, I will going to introduce Intermediate Value Theorem, which is a very important property for continuous functions. So here is Intermediate Value Theorem. Later, we are going to use this theorem to find the root of equation. What does the theorem tell us? So first, we have two conditions for a function. The first condition is continuous on a closed interval. The second condition is f(a) does not equal f(b). And then we have one result. The conclusion is this. For any number n between f(a) and f(b), so this n we call the intermediate value, okay? And there exists a number c in AB such that fc equals n. What does it mean? Which means f the function can reach to the intermediate value n. Why? This value is between fa and fb. Any value between fa and fb, we can find a number in AB so that the fc equals n, which means the value of the function can reach to this intermediate value. What does it really mean? So let's go to look at the graph. It will give us a meaning, exact meaning, or give us a proof for this theorem. And we have a function. We set two conditions. Let me see. The first condition, f continues on a closed interval. F is continuous in AB. Of course, the left endpoint is continuous from the right, and the right endpoint is continuous from the left. Okay, this is the first. Continuity is the first condition. The second is fa does not equal fb, which means what? Which means if I simply draw this is the starting point, if this is the starting point, this is the end point, which means what? fa does not equal fb, which means these 2 points are not at the same level, not at the same horizontal line. Okay, and then the conclusion is any number, any intermediate value between fa and fb. Okay, so n is between fa and fb, and then we can the value of the function can reach to this intermediate value, which means if we draw a horizontal line, at least we can find one intersect point, right? So at least intersect at least once this horizontal line and the continuous function. If this is the intersect, so for the x, if we're going to see x coordinate, so it goes down. Coordinate is here. So this is c, right? So we find the c, what? fc equals n, which means f can reach to n. If you look at the graph, it's very easy to understand why. Okay, if we imagine y equals n is a kind of river, okay, and this starting point is on one side of the river. If you want to go to another side of the river to the end point, you imagine you have to cross the river at least once, right? When you cross, and this point is you can find a c, fc equals n, which means the function reach to the value n. Okay, does this make sense? Imagine if the function is not continuous, if you can jump, or if we have a gap at this point, imagine, so we never reach to n of the value of the function, right? Okay, let me see. Okay, two conditions. The first condition, continuous. The second condition is fa does not equal fb. Okay, no matter fa greater than fb or fa less than fb, that's okay. Okay, and then the conclusions, any intermediate value, and draw horizontal line, you can find one c at least. fc equals n. Okay, we can reach to this intermediate value. We have a special case, and later we will use this special case to do approximation for a root of equation. Okay, and what the special case? So this time we look at it. This graph is good enough. The first condition is the same, f continues on AB, close the interval. The second condition we change a little. So dear fa does not equal fb. However, we have another fa times fb less than 0. If in our graph fa greater than 0, fb is less than 0. So fa times fb should be less than 0, right? This which means opposite signs of fa and fb. If the sign are different, of course, fa cannot be equal to fb, right? So therefore, the intermediate value theorem works. So this is the starting point, this is the end point, these 2 points is on the different sides of y equals 0. So given n equals 0, okay, draw a horizontal line. See, at least the 1 intersect the point we find. So this point, the x coordinate, we call it c. So fc equals 0, right? N is 0 in this special case. And this c we call it a 0, or a root of the equation fx equals 0, right? So c is a root. Therefore, what? We can find at least one root between a, b. So the result is fc equals 0. This equation has at least one root in a, b. Of course, a, b is what? Is open interval. Keep in mind, we cannot reach from at a or reach from b. We should be between a and b. Okay, we can find at least one. Why? Because start a, end at b, and the middle, of course, not include a, not include b. In the middle, we should find 1 point. So f is equals 0. And this is a special case of intermediate value theorem. And can you see? And this case we just used to find a 0 of equation. And this is the most important application for intermediate value theorem. Let me see the first example. Then later I have another example show you, okay, how to use the intermediate value theorem, especially for the special case we just discussed. And these questions use the intermediate value theorem to show that the equation has a root in the specified interval 2 to 3. What does it mean? We did not see a function. Of course, you do a little bit of change. If minus x plus square root of x both sides, you will find ln minus x plus square root of x equals 0. That's exactly fx equals 0. So we can set up f equals 0. Therefore, these questions ask us to prove, okay, fx equals 0 has one root in 2, 3. Can you see? So the function has one root, at least one root in a, b. Okay, what do we need to do? We need to verify 2 conditions if we are going to use this special case. The first condition is f is continuous. Okay, we need to verify. The second condition is fa times fb less than 0, or is the opposite signs for fa and fb. Okay, we verify these 2 conditions. If we successfully verify it, then we have the conclusion. fc has one root, at least one root in AB, right? So we proved that. All we need to do. So we just said we need to set up the function first. Let me set up the function. And what is the function? fx equals 0. So we need to minus x plus square root of x both sides. We can define f equals 0, right? So what is f? We define first. So fx is this. We let fx equals ln x minus x plus square root of x. Okay, this is the function we are discussing. And this equation, which means fx equals 0, right? We're going to find the root of the equation. We are going to find the 0 of the function. Okay, so now for this function, so we need to verify 2 conditions. The first is continuous. The second, different sign at 2 and 3, right? So first, continuous. We say this is continuous. Why? Because this function is a combination of basic continuous function. Ln, the logarithmic function, continuous on the domain. X is linear function continuous. Root function is continuous on the domain. Okay, put it together. The domain, of course, is x greater than 0. So what we discussed from 2 to 3 is in the domain, right? So this function is continuous. Let me write a little bit. So probably you can say because combination of continuous function are continuous, right? So let me write here. Combination of continuous functions are continuous. Okay, continuous functions. This function we defined is a combination of continuous functions, so this is continuous. Therefore, f(x) is continuous, and f(x) is continuous. Continuous in the domain. The domain is greater than 0, so cover 2 to 3, right? It's continuous on 2 to 3. We have to put okay, this closed interval. Why? Because the theorem, so we need to verify the function is continuous on this, which means continuous in the open interval 2 to 3, and right continuous from the right side at 2, continuous from the left side at 3. Of course, this is satisfied because the function is continuous for any x greater than 0 in the domain. Okay, the first condition good. The second condition, verify f at 2 and verify f at 3 has a different sign. Okay, and we're going to do calculation for f at 2 first. If you use your calculator, so you will get this 0.107 is greater than 0. Okay, positive, and f at 3 should be negative. Let me go to see f at 3 is rounded to this negative 0.169 is less than 0. So that's good. Condition 1 continuous satisfied. Condition 2 different sign satisfied. Therefore, we by the intermediate value theorem. So f(x) equals 0, or this equation has one root, right? Okay, we have a conclusion now. So by the intermediate value theorem. Okay, and f(x) equals 0, or you say f(x) equals 0, and this is exactly this is the original equation. Okay, ln x equals x minus square root of x. Okay, this one has one root, at least one root. Okay, in the open interval 2 to 3, and the results we get from the intermediate value theorem. So the first questions, and all we need to do to prove there is a solution, all we need to do so verify the first continuity works. The second, different sign, okay, on the end point. So look at it. The theorem is so super easy to use. And the second questions is similar. We have an equation. So first, so in part 1, because later I have part 2, I will ask you to do approximation. Okay. So part 1 is prove the equation has at least one real root. Okay. Of course, real root, we need to find the root. Okay. The same. So what to do? We need to use the intermediate value theorem, right? So to find the 0, you need to define function first. Of course, we minus the right side, both sides. Okay, so we will define a function, which means 100 times this minus 0.01 times x squared. This is a function. This function has a 0. Okay, has a 0 word. So this is a little bit of trouble. And the first questions already give us an interval. All we need to do just verify the function is continuous and has different value. Okay, has different sign on the end point. This time we don't have an interval. What to do? We need to make an interval for ourselves. Okay, all we need to do is just try. But first, whatever we need to do this, we set up the function. Let me set up the function. So the function is this. Let f(x) is this. Is the left side e negative x over 100 minus the right side as 0.01 x squared. And this is a function. And easy to see, this function is continuous, right? Because the exponential function is continuous and the power function continuous linear combination, so we have a continuous. That's good. The first condition definitely easy to verify. So how about the second condition? What does the second condition mean? Okay, we need to explore this function first. Let me explore what that this function, what the function will look like. Okay, so this negative x. So the first part is decreasing, right? We look at it. Okay, how about the functions increasing or decreasing? The first part is decrease. The second part, if negative, so x squared is what? If we look at whatever, if we look at the right side, x greater than 0. The right side is increase, so negative, so decrease. You can imagine. So put the decrease plus the decrease, so the function is decrease. Of course, it's for all the x greater than 0. For all the x greater than 0, the function is decrease. Decrease to where? Okay, you can imagine when x is very, very big, like a million, 10 million. So of course, this is definitely goes to a very, very large number, but negative, right? Which means what? If we take a limit, this goes down to the negative infinity. Okay, goes down to negative infinity. How did about the beginning? All we need to do is to find one root, right? Which means the function has 1, 0. Now we know the value of the function will go, but no, go to negative. Okay, another part, we need to find the value is positive. If we find a 1 positive, 1 negative, in the middle we can find the 0 of the function. You have to try. Okay, so I already tried. If we pick x is 0, so this time is 0. Pick x is 0, so this is 1. 100 times 1, 100 minus 0 is 100. Imagine, which means f the value at x equals 0 is 100. 100 is a positive value, right? Okay, which means this function at 0 is positive. At whatever another number, like you pick 100. F at 100 is negative, definitely. Okay, from 1 positive go to negative. So in the middle we can find one root. This is the basic explore. So have you get it? And let me write it down. So we have we already make an interval is from 0 to 100, right? You can make it like from 0 to 1000 or whatever. Okay, so I will already make 1. So we can verify the two condition works. The first condition is easy. f(x), what we define is continuous, right? Is continuous on here 0 to 100. Okay, we just say this is the most important. We find 0 to 100. Why? Because f at 0 is 100 greater than 0. If we plug 100 inside, we will get a negative value. That's why we use this interval. Okay. So the second condition is f at 0 and 100 are different value. Okay, a different sign. I was going to write f at 0 equals 100. We just find. And another is what? This is greater than 0. Another is f at 100. Okay, this time you have to use a calculator. Use a calculator, already get it. It's negative 63.2. It's less than 0. That's good. So can you see positive or negative in the middle? We can find at least 1, 0. Therefore, by intermediate value theory, intermediate value theory, We already proved that the first is true. Okay, and fx equals 0. Fx equals 0. All this is equal to the original equation. Is 100 times e negative x over 100 equals 0.01 times x square. This equation has one root, right? Okay. Has a root what? In 0 to 100 open interval. Okay, the first part we prove. Okay, this is the normal way. The second part, can we look at it? So going to find what is the what's the root. We just say what? We just say fx, this function we defined has one root in 0 to 100, right? So we see infinite points. What is the exact number? Or at least we need to do approximation. Okay. So here I already wrote down. I'll give you the basic idea, and later I will show you how to reach to these results in a calculator. Okay. So we already have the function, right? And we already know the function has one root at least in 0 to 100. Okay, 0 to 100. So now we need the what? We need the calculator, and then we use the calculator to gradually zoom in 0 to 100, and then to find the approximation. This is a very old method. In the future, we have a new method we call the Newton's method. Okay, it's very efficient for us to find the approximation of the root in the future. But here we have to use the very old method. It's this way. How to zoom in? Let me give you. The original is 0 to 100. We know we have one root, right? And then draw a function, and then you cut the function pieces, and then we will find use the intermediate value theorem. We will find 70 is positive, 71 is negative. Now we know the root should be in 70 to 71, right? Intermediate value theorem give us we have a root in 70 to 71. Now from here repeat the procedure. So how to do? And the cut and draw a graph in 70 to 71, and then we look at 70.3 to 70.4, and this is positive, this is negative, so the road goes into this small interval. This is just zooming in. Okay, imagine we have a graph, just zooming in from the original 100, zooming in to 70 to 71, then zooming in to 70.3, 70.4 again. Okay, I will going to show you how to exactly zoom in, and then we zoom into this interval, and then we zoom into this interval. One more time we zoom into this interval. Now we can stop. Why? You can imagine. So 70.3467, 70.3468. Okay, see these two number A, B is already very close. Okay, and the road between this is already reached to correct to 3 decimal places. Okay, why? No matter you pick a 7 or you pick 8 at the last digit, what do you get? It's always 3, 4, 7. 3, 4, 7. Can you see? Okay, it's approximated to 70.347. Is already reached to 3 decimal places. So we can stop. You can imagine if the question asks you go to 5 decimal, you need to zoom in a lot of more times. Okay, you need to zoom in a lot of more times. And here is the big idea, of course, how to gradually zoom in. Zoom in the graph in the graph calculator. You need to set up something. We have to set up the window. Okay, how to set up the window, of course, is kind of is a little tip we need. So let me see. Here is the window I set up it. So we need to set up a minimum x, maximum x. Okay, the domain. We need to set up the minimum y and the maximum y, which means the range Okay, and then the window is set up in this way. I also need to set up the scale. What does it mean? Because when we set up the scale, we can look at the 0 belongs to which part easily. Okay, let me show a little. The first we set up 0 to 100, draw graph. That's true because we know the 0 is between these one, right? And then the minimum, the maximum y is easy to set up because of this. Because from what we did the calculation before, 0 is 100 and 100 is negative 60. So if I set up a negative 100 to 100, that's good, right? So that's why I set up a negative 100 to 100. Okay, and then we draw a graph. Why I set up the scale is 10. Okay, and I will show you later. When we draw a graph, we set up the scale. We can easily to look at where is the solution, where is the root. Okay, and then we trace. We will find the 70 and the 71. Of course, 70 is greater than 0. 71 is less than 0. Therefore, now we zoom into this small interval, and we have a road inside this interval. And what is the minimum and the maximum y based on the value? Okay, based on the graph. And I set up a negative 2 to 2. See, can you see? We set up in the symmetry. Okay, negative 2 to 2, negative 100 to 200. Because in this way, it's very easy to look at the graph. Probably, if we change the questions, you will set up another way. Whatever, the y value is based on the graph. And now I set up the scale is to 0.1. What does it mean? Because the range is 1. I set up the scale is 0.1, which means I cut the range 70 to 71 into 10 pieces. And then I look at the 70.1, 70.2, 0.3, Okay, so we have 11 points to look at. Okay, and I found that this point and this point, this positive, this negative. Therefore, what? Okay, zoom in from 70 to 71 now to this small interval. Okay, again, this y value is based on the graph. And the new scale is based on I want to cut this range or this interval into another 10 pieces, and then continue to zoom in again. Let me set up the calculator and show you how to zoom in this way. And whatever the final, if you zoom in to the last, you already get the solution, right? Let me set up my calculator. I will show you how to do in the calculator. So here is my calculator. I use 83. If you have 84, it's similar. I will turn on my calculator. First, draw a graph and set up the function. So y, right? Y equals set up the function. Let me tune so you can see. Wait. Yes. And this function I already typed. This function is exactly what the function we defined. We have that function. We define this function into y equals. Okay, I already have the function. And then we need to set up the window, right? We need to set up the window. Okay. So what is the first setup? Is 0 to 100. Okay, and the y value is this, and the scale is 10. What we're going to do is the window. Click the window. I set up a minimum 0, right? And the x minimum 100. The scale is 10 because I cut 0 to 100 to 10 pieces. And the y minimum is negative 100. Y maximum is 100. And the y scale resolution is okay. And then we're going to graph. Let me do again. Okay, so I will going to graph. Can you see? This is the graph already. Why I set up the scale? You know, this is 0, this is 100. So now I look at the 0 probably around like 70, right? This is y. I set up the scale so I can so I will know roughly where is the road. Okay, 70. Let me trace. You can do this. Okay, you can click trace. Okay, so I will going to click trace. and probably, can you see this? Okay, you move left or move right, you can trace the point on the graph. So probably here is positive, right? 70 is positive still. One more, can you? 71 is already go to negative. Of course, this is not exactly 71, but from here we just zoom in. By trace, you know probably 70 is positive, but 71 is negative. If we want to exactly prove is this, we just type 70. I just type 70, okay, which means x equals 70, and okay, x equals 70, y value is positive, right? Definitely. How big is 0.6? And then let me type 71 to look at 71. Okay, then enter. Negative. That's why we find 70 to 71. Can you see? And later I set up, we zoom in to 70 to 71. This is the reason why we get it. Okay, and what is the new range of y? -2 to 2. I will show you why I get it. Can we type 70 again? 70. See, is what? It's 0.6. 70 is 0.6. 71. I type 71. -1.2, which means the range probably is -1 point something to point something. Okay, and I will set up -2 to 2 because it looks as symmetry. Okay, it's easy to have a look. So now good, I already get it. And x minimum, y minimum. I zoom into this, and the range we set up this. Okay, let me go to the new window. X is going to 70 to 71, 70, 71. So how about the scale? I like to cut it like just 10 pieces, whatever. Okay, I cut it in 10 pieces. So each piece 1 is the range. We cut it into 10 pieces, so I have 0.1. So I set up 0.1 is the scale. So y minimum, you know, is -2, right? So we set up -2. The +2 is for y. See, and we set up everything. Now we're going to graph again. Okay, so can you see the graph? Yes, it's already done. So the left is 70, right? The right is 71. So we probably can find 70.1, 0.2, 0.3, right? So around the 70.3. This is the function. Okay, why we need to set up a scale, but we have to trace. Look at this around the 70.3. So I have to do what? Type 70.3 to check the value, positive or negative. I will enter. So it's how many? It's very small. It's 0.08. Okay, I get 0.1. Around the 0.1 is positive. So 70.4. How we going to do 70.4? And this time is a negative 0.1, which means what? So we find that we zoom in to 70.3 to 70.4. Can you see? Why I set up the new zooming in interval is 70.3 to 70.4. What is the range? Of course, we just find, see, -0.1 to 0.1, right? Around that. So I set up -0.1 to 0.1 is the y range. And the scale, of course, I was still going to cut 10 pieces. Let me set up one more time. Going to window. X minimum 70.3, 70.3, 70.4. Okay, this X. Scale this time is 0.01. I still going to cut 10 pieces. 0.01. The y minimum is -0.1 to 0.1. -0.1 to 0.1. Yes, we set up everything, right? And then going to graph. That's just a repeat the procedure. So this time what do we get? 70.3, 70.4. Each scale is 0.01, right? So this is 70.3, 31, 32, 34, 35. See, it's very easy to see. It's 70.4, right? 1, 2, 3, 4. Okay, so this is a 70.34. This is 70.35. That's why I was zooming in into the new interval 70.34 to 70.35. Okay, and now all the other procedure is the same. Just repeat two more step, you can go into the final. Yeah, that's all. Thank you.